Access to fresh water is one of the largest drivers of creating a modern society. But what allows everyone access to seemingly endless supplies of potable water? It depends on where you live, but chances are behind your tap, there's a municipal water treatment plant. There are two main types of water treatment plants: drinking water or wastewater plants. We'll be focusing in on drinking water plants here, but if you'd like to learn about how wastewater is treated, you can watch the video linked in the upper right here. The question still remains, how exactly does one treatment plant take dirty river water or well water and turn it into water that is safe to drink? It involves a lot of processing, using chemicals, filters, and removing all of the toxins and hazards from a given source. The entire process starts with something called coagulation and flocculation. All drinking water has to come from somewhere, usually being freshwater lakes, rivers, wells, or streams. In these water sources, there's going to be some amount of sediment as well as organic materials in the water. These particles of sand, bacteria, dirt, wood, etc., they all have to be removed before the water can be sent out to city residents. To do this, chemicals called coagulants are added to the water. These chemicals, such as aluminum sulfate or ferric chloride, work to help the particles in the water congeal together. Essentially, these chemicals have the opposite charges of suspended solids, like clays or silts. When combined, the charges of the particles are neutralized, allowing for them to stick together. Coagulants are often added to the water right at the inlet of a drinking water plant, where the water then goes into mixing basins called flocculation basins. In these basins, the solution of water and coagulant will slowly be mixed together to form what are called floc particles. After mixing for a set amount of time determined by water quality in the flocculation basins, the water is moved to sedimentation basins. It's in these holding tanks where the water sits for the floc particles to begin settling out at a faster and faster rate, which is the intended goal of this process. By simply adding and mixing these chemicals into the water and letting that water sit, a large portion of the sediment will settle out to the bottom as sludge, which can be taken away to a landfill or holding facility. The floc particles are ultimately removed from the bottom of basins, and the clean water, being the cleanest at the top due to the settling particles, flows over weirs to the next stage in the process. In some plants, engineers actually use dissolved air flotation tanks in place of sedimentation basins. In these cases, air is pumped into the bottom of the tanks, creating a cascade of tiny bubbles. As these bubbles float to the surface, they take floc particles with them, forming a film of floc on the surface of the tanks. Then, a sweeper arm pushes the floc into a collection basin where it's taken to a handling facility. In dissolved air flotation tanks, the clean water is taken from the bottom, where the least amount of floc is. When it comes to designing wastewater treatment plants, engineers will vary techniques based on the water source and how they want their final water to taste, feel, or otherwise be treated. The only regulation is the quality of water being pumped to the city, and in most cases, it doesn't matter how plants get the water to that point, which allows civil engineers a lot of creative freedom in the process. After the majority of solids are removed from the water during coagulation and flocculation, followed by sedimentation, the water flows over weirs to the next step, filtration. The water at this point will start looking clear, but there will still be bacteria and very small suspended solids in the mix. The filtration process will seek to remove the remainder of the suspended solids and bacteria to further bring the water up to snuff. Nearly every potable water treatment plant will use a sand filter for this process. Even in plants where engineers may not think it's needed, often sand filters will be added simply for extra measures to ensure clean water at the end. Sand filters are exactly what they sound like, a basin of fine to coarse sand that filters water. It would theoretically be possible to treat drinking water with only sand filters, but that would result in frequently clogged sand filters, resulting in lower efficiency and more cleaning time. These sand filters can be set up in essentially two different ways. Either the water flows from the bottom and exits the top, or the water flows from the top and exits the bottom. Each layout presents its own set of unique problems, but the most common technique is actually for the water to flow from the bottom to the top. Sand filters aren't highly technical. Water just passes through them and particles get caught as they run out of space to flow through. However, while not highly technical, sand filters are highly efficient. Water flowing out of sand filters will need to have a clarity of around less than 0.3 nephelometric turbidity units, or NTU. try saying that 3 times fast, or whatever local code is used for water clarity. This measurement is essentially just a way to determine the number of particles still remaining in the water, or turbidity. Many treatment plants will also pass water through activated carbon basins, which you can essentially think of as giant Brita filter tanks. Activated carbon particles have hundreds of tiny pores on them that help remove the tiniest of sediment and bacteria. This process isn't wholly necessary, but it helps improve taste and odor, often a desired trait for city residents. At this point, the water should be mostly crystal clear, but there still remains some residual bacteria. That leads us to the next step: disinfection. There are 3 main ways of disinfection in the water treatment process, which can be used individually or in combination with one another, depending upon design. First, chlorine or chloramine treatment. There's ozone treatment, and finally, ultraviolet radiation treatment. In the US, the main method of disinfection is by adding chloramines, or chlorine-based compounds. These compounds, such as chlorine dioxide or monochloramine, work to kill microorganisms. One downside to this process, though, is that these chemicals can react with other organic material in the water to create disinfection byproducts. These disinfection byproducts are harmful to human health and have to be prevented or mitigated. This extraneous reaction with other organic material is also why chlorine disinfection must come at the end of the treatment process. If added at the beginning, an abundance of disinfection byproducts would be created, causing a plethora of issues for the engineers and plant operators. Even with all of this, chlorine is used mainly because of how it kills pathogens. It not only kills any pathogens in the water at the plant, but residual chlorine levels also remain in the tap water, killing any contaminants that might get introduced after leaving the plant. Most cities or states will have maximum or minimum chlorine levels in the treated water in order to keep both the water treated and city residents safe. The other most common method of treatment is ultraviolet radiation. In this process, UV light is shined through the water, which scrambles any bacteria's DNA. This doesn't kill the bacteria, but it makes it impossible for them to reproduce, thus making them harmless. The main downside to this disinfection process is that it isn't residual like the chlorine, meaning that any bacteria introduced to the water after this process can't be treated. Finally, we're left with ozone treatment. This process involves adding ozone, O3, to the water. Called ozonation, the ozone kills the bacteria in the water as well as improving the taste and odor. In most cases, this treatment process also requires that a chemical be used to remove any ozone at the end, such as sodium bisulfate, as not to cause any harmful effects to the city's population or anyone who might drink the water. After the water is treated, in any one of these 3 disinfection processes, it's ready to be pumped into a city's pipe network for delivery to your tap. The water flowing out of a plant is tested for various levels of chemicals, particles, and other qualities all outlined in a plant's permit. This permit, set by the governing agency, regulates water quality and holds the treatment plant accountable in the treatment process. At this point, all the water is fit for human consumption per the permit, and the treatment plant is tasked with keeping it flowing through the pipes in your city. Constant pressures of 40 psi must be kept at the outlets of the water in the system so that in areas of high elevation in the pipe network, the water retains residual pressure. 1 foot in water elevation is directly correlated to an increase or decrease of 0.433 psi. So as water is pumped throughout the city, its pressure at any given point of differing elevation fluctuates. Positive pressure always has to be achieved as to not let any external water in the ground flow through pipe cracks or joints. This would contaminate the entire system and is one reason why you might experience a boil water notice. Essentially, that means engineers have reason to believe that somewhere in that city's pipe network dropped below the required PSI and water or contaminants might have infiltrated the system. Massive pumps at the treatment plant supply pressure to the system through constant operation. Some of this pressure can be stored as elevation in water towers, which can give pumps a backup in emergencies or fire flows. In a lot of cases, water towers allow the pumps at the treatment plant to run at a a constant rate, which increases efficiency and removes downtime problems. This combination of pumps and water towers allows your tap to remain flowing and otherwise allows you to live in the comfort of your own home. Civil engineers and treatment plant operators work around the clock to provide clean water through water treatment plants. At this point, we've taken a look at the most common potable water treatment techniques, but there are tens to hundreds of other deviations we haven't discussed. This draws back to one of the coolest things about water treatment plant design. You're able to use any number of creative solutions to clean the water, and as long as it comes out clean, you've done your job well. Don't forget about the thankless job of being a water treatment plant operator, though. These men and women work around the clock to keep treatment plants running 24/7 so you can always have fresh water. A lot of time, money, and effort goes into making sure that you can have that nice glass of water on demand.